And even helium is made, mostly in stars. So basically, this whole like being metal rich and silicate rich is kind of special. So we should be thankful we have this on Earth. Earth is very special in that sense. So these metal rich and silicate rich bodies close to the sun are the terrestrial planets. Since materials with low volatility tend to be dense, the terrestrial planets all have high densities. So let me tell you about some of our densities. So Mercury's density is 5,400 kilograms per meter cubed. Venus's density is 4,200 kilograms per meter cubed. Earth is also 4,200 kilograms per meter cubed. And Mars is 3,300 kilograms per meter cubed. So Mars is less dense than Venus and Earth. So I think I mentioned earlier at one point that Venus is a lot like Earth, actually, in size and apparently the density. So if I had to pick another planet to go to, it would be Venus, but unfortunately, I believe its atmosphere is rather poisonous. Stinky. Yes. Okay. So this is where I listed off the uncompressed densities of the terrestrial planets. In other words, this is the density of the planet would have if it were not squeezed to a smaller volume and higher density by its own gravity. So these are the uncompressed densities of terrestrial planets that I listed off, as in when they're not squeezed further under its own gravity, that would be the density. Note that the uncompressed density of the terrestrial planets decreases. So note that it decreases with increasing distance from the sun. Mercury had the highest density and Mars had the lowest. It is interesting, however, that the uncompressed density of the moon, our moon, is only 3,350 kilograms per meter cubed, much less than the Earth's uncompressed density, despite the fact that they're at the same distance from the sun. The unexpectedly low density of the moon is a consequence of its unique formation history, which we'll talk about later. In the outer part of the protoplanetary disk containing planetesimals of both high volatility and low volatility materials, larger bodies are able to form. Once these protoplanets reach a mass of around 15 Earth masses, they're massive enough, given the low temperatures in the outer disk, to retain hydrogen and helium. So they're massive enough to retain hydrogen and helium, massive enough given that the temperatures are lower out there. They're massive enough to retain hydrogen and helium. Since hydrogen and helium are the most abundant elements, being able to hang on to them permits the Jovian planets to grow to much larger masses than the terrestrial planets. Protoplanets grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. So they grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. During and immediately following this early phase of coalescence, the interior and surface structure of terrestrial planets are changed by several processes, among them chemical differentiation, cratering, volcanic flooding, and slower processes of surface evolution. Chemical differentiation is the process by which dense elements sink to the center of terrestrial planets. So how cool is this? So by the way, another reason why I don't know much about the Earth is because that's geophysics. And I did not do geophysics. So studying the Earth, etc., that's a whole nother field. We will learn about it a little bit here today, but this is really a much larger field. Okay, so protoplanets grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. And then there's pretty much after the protoplanets are formed from the coalescence, there's a bunch of interior and surface structure of terrestrial planets. There are a bunch of processes by which the interior and the surface structure of terrestrial planets are changed. And